Welcome to the Chapter 16 lecture. This one is going to be all about light. We're continuing with the idea from Chapter 14, which was waves. And so we'll see that light does have a lot of wave-like properties, but we'll also see that light has some properties that are more easily described by thinking of it as a ray or a string of particles. Anyway, this is introduction to light, and then the next three chapters after this, 17, 18, and 19, are all going to expand upon the details of light. And so this one is really just kind of an overview or introduction to light, and then those will go into a lot more detail. Okay, so the first thing is you have to accept the fact that when you do different experiments under different circumstances, sometimes light can act like a particle, which is called ray optics. That's the study of light as a particle. And sometimes it can act like a wave, and that's called wave optics. And then there are other properties that it has that are true of it, regardless of which way you think about it. For example, the speed that it travels. Whether you think of it as a wave or a particle, the speed that it travels is the same regardless. So we're going to start exploring, just in brief, these three different categories of properties of light. So the first thing we'll talk about is the ray model of light. If you think of light as a ray, it has to come from somewhere. So the two possibilities where it can come from are either a luminous source. A luminous source means the light is emitted from that source. So this is the actual real source of all light, are always luminous sources. So some examples of that might be the sun, maybe a candle, maybe a light bulb. So anything like that, where the light, that's actually a source of light being created. And then the second way that light can come off of something is called an illuminated source. And so an illuminated source means the light is coming from that object, but it's reflected off of that object from somewhere else. So the vast majority of things that you see are actually illuminated sources. For example, when you look down at your piece of paper, it's not actually emitting any light of its own, but the light from, say, the lights above you are coming down, striking the surface, and bouncing off. So it's a source of light, but it's illuminated by something else. Whereas your computer screen, where you're probably watching this video, is actually a luminous source. It is emitting its own light. Just two fun pictures that helps you visualize light as a ray. And then if you are thinking of light as a ray, then it's going to travel in a straight line until it strikes another object. Not to confuse you, but later on, when we treat light as a wave, it may not always travel in straight lines, but when you're thinking of it as a ray, as a particle, it's going to travel in a straight line. Okay, so again, thinking of light as rays, what happens when it hits things or interacts with things? So unless light interacts with small things, I'll quantify this in a second, then it will travel in a straight line and either bounce off or pass through objects that it encounters. When it hits things that are very small, and by very small, I mean the actual wavelength of the light. So the wavelength of the light is probably like less than a micrometer, so maybe like 400 to 700 nanometers, which is really, really, really tiny. So when it's happening to interact with everyday objects, it's never interacting with things that are that small. And so for the most part, in everyday objects, it can be treated as a ray and traveling in straight lines. In Chapter 19, though, we will go into the phenomenon of what happens when light hits something that's nearly its own wavelength, and it gets kind of fun and complex. But again, since everyday objects are much larger than this, we typically observe ray behavior of light in our everyday lives. So here's what happens. Light travels in a straight line, and then when it hits a surface, there's some different things that can happen. It can reflect, which means bounce off. Okay, so reflection here is where it bounces off the surface. So it's coming in this way, hits a surface between two things, and then bounces out. So maybe this is air, and this is a table. You know, the light is going to hit it and bounce off. The other option is that it can refract or pass through. We don't call it transmission because refraction includes transmission plus some things happen to it when it goes through. So you can see this light ray right here. It kind of changes direction just a little bit, ever so slightly bending that way. When light passes from one material into the other, it does refract, which is something we'll learn about in Chapter 18, and that's the bending of light as it passes through. But again, we're going to ignore that for now. But in a particular medium or material, the light does travel in a straight line. It's only going to bend like that when it passes through from one material to another material. And that's something, yeah, we'll study later. So When it's inside of an object, whether that object could even be air, or some other more complex object or more dense object, there's two things that can happen. It can get scattered, which means it bounces off particles in the material, like this. So maybe it hits an air particle and bounces in a different direction. An example of that might be, scattering might be if you have some mist, and you have a laser shining through that mist. The laser light will hit those misty particles and bounce off in different directions, allowing you to see the laser light that you wouldn't normally be able to see. And the second thing that could happen is it could be absorbed. So sometimes when you shine light on an object, most of it doesn't reflect. Most of it actually goes into the object and is absorbed. An example of that is black objects. So very little light is reflected from black objects. And all objects are the source of light, either illuminated or luminous sources. Okay? So when light hits an object, based on the things we've just said, there's ways you can classify a material based on what happens. So if the material is considered to be opaque, that means the light is reflected off. I'm going to add here, or absorbed. So opaque means the light doesn't pass through. The way it could not pass through is if it's all reflected or if it's all absorbed. I apologize, I probably should have had that typed in, but that's opaque. Transparent means the light passes through undisturbed. It does bend a little bit, as we just saw, but it doesn't scatter really. It just goes in and then straight through out without scattering much. And then translucent, the light does pass through but is distorted, and I'll put here scattered. So there's a lot of scattering. So some light is going through, but it's getting shifted off in different directions. So you could think of some examples, like opaque would be a wooden door. The light does not pass through. It either is absorbed or bounces off. Transparent is completely see-through, if you will. So this is like maybe polished glass. If you put up a polished glass in front of you, the light is going to pass right through. And then translucent might be something like a lot of frosted glass doors, maybe for your shower, or a shower curtain that's kind of somewhat see-through. Like, it allows a little bit of light through, but the image is distorted because the light is getting scattered or spread out a lot. And so opaque is easy to remember because it's different. Transparent and translucent are pretty similar. Both of them let the light through, and they both kind of sound similar. So I want to give you a trick to help you remember the difference. Your parents probably want to know everything that's going on without any fuzzying of the details. So that's how I remember that the light passes through completely undisturbed. The parents don't want to have any distortion on what's going on. The parents want to know what's going on. So transparent is completely undisturbed, and then translucent is the other one, where the light passes through, but not all of it goes straight through. Some of it scatters. Okay, so those are the concepts of light. Now we can start to quantify light and talk about numerical values and start some calculations. 1 second, someone just came to the door. Okay, all is good. So luminous flux is the rate at which light energy is emitted by a source. So say you have like a candle or something like that. It's putting out a certain amount of light particles. You might have heard of them called photons. That's a particle of light. It's putting out a certain amount of light per unit time. Obviously, the brighter it is, the more light it's putting out. And so we can quantify this using the SI unit, lumens. So lumens are the amount of light energy per time. Now, a lumen is not the same as a watt. A watt, remember, is also energy per time, and a watt is joules per second. So lumens are not watts, but they're kind of like watts. And there's a conversion factor that depends on the type of bulb. But if you're purchasing a light bulb that's a certain power consumption, like say a 100-watt light bulb, puts out roughly 1750 lumens of optical energy, or of light energy, if you will. And so depending on what type of bulb, there's different efficiencies. So for example, if you've gotten CFL bulbs or some LED bulbs, different wattages will put out different luminosities. So there's not a direct conversion factor between watts and lumens, because not all bulbs have the same efficiency. So you just have to look it up for a particular type of bulb. But to see which one is going to put out the most light, you want to look at the lumens. To see which one is using the most energy, electrical energy from the wall where it's plugged in, you look at the wattage. So what you want is a low wattage, high luminosity bulb, and that's going to give you the most bright amount of light for the smallest amount of money. If you're comparing all light bulbs of the same type, like all incandescent, then of course more wattage is going to give you more luminosity. So luminous flux is the amount of light, and the symbol we're going to use is P. I agree that that is really annoying, but that's the way it is in the book, and I'd rather not divert from that. Okay. The next thing is luminous intensity. This is an alternate way to measure the rate of light energy being emitted, and honestly, I'm not sure in which case you would want to use this, but the book definitely talks about it, and the book gives you some problems in candelas, so I thought I would mention it here. Essentially, the luminous intensity is the same physical type of quantity, but it's dividing the original one that we saw before this, luminous flux, by 4 pi. And so that's candelas. So if you know the luminous flux in lumens, you can divide by 4 pi to get the luminous intensity in candelas, and vice versa. If you know the candelas, you can multiply by 4 pi to get the luminous flux. So they're both ways to measure the same thing. You could think of it as like, I don't know, calories and joules are two different ways to measure energy, just two different units that have a conversion factor between them. And this one is a set conversion factor, 4 pi. If you're interested in why it is what it is, it has to do with the sphere and the surface area and the light projected onto a 1 square meter surface area inside of a shell. It's kind of, I don't see a lot of value in spending time worrying about that. But if you want to, it's in the book, in this chapter, or I'm happy to discuss it in class. Okay. And finally, an equation that's actually going to allow us to calculate the amount of light hitting surfaces and see how bright things are. This is much more useful because when you're designing buildings or trying to see stuff, it's actually the illuminance, which is the amount of light delivered to a surface per unit area, that allows you to see stuff, right? So you can tell that if you have a certain light bulb, say 100-watt light bulb, whether or not that's enough light for you to see depends not only on how much light it's putting out, but also on how far away it is. So this equation here for the illuminance, symbol E, so the illuminance, and this is again for point sources, not again, but I guess I'll tell you for the first time. This is for point sources. So this works well for light bulbs, for the sun, for candles. If you think about it, most sources of light are point sources. So this is quite effective, actually. Anyway, the illuminance, or the light hitting your surface area, equals the luminous flux, P, that's the total amount of light, divided by 4 pi r squared, where r is the distance away. So the farther away you get, the less light there's going to be actually hitting your surface. I mean, that makes common sense. If you move the light farther away, less light is going to hit your surface. And in fact, it's proportional to r squared, so that if you move the light twice as far away, you only get 1/4 as much light. If you move the light 5 times farther away, you only get 1/25 as much light hitting your surface, and that has to do with the way that it spreads out in a spherical direction on all directions, and I'll derive this formula on the next slide. The symbol for illuminance is called lux, with the symbol is Lx. That's the same as lumens per square meter. Lumens per square meter are, and I'm happy for you to write lumens per square meter. In this chapter in particular, I find the units to be a bit cumbersome. We've got lumens, candelas, and lux, which none of the three are something that typically students have heard of or are comfortable with prior to coming into this class, and I myself am not even all that comfortable with these kind of units. I'll often have to check and see, is it lumens or is it lux? So just write it down and keep track, and if you want to use lumens per meter squared, you're permitted to. Lastly, to find the total amount of energy hitting a surface, you should multiply the illuminance, which is per surface area, times the size of your surface area, right? So if you've got a 8.5 by 11 sheet of paper and you want to know how much total light is hitting that piece of paper, you can multiply the illuminance on the paper times the surface area. So obviously if you have a bigger surface area, you're going to have more light hitting it. Okay, so let's derive this previous formula. The formula we're trying to derive is E equals P over 4 pi r squared. It's very easy to derive just using geometry. So here's your point source of light. And when it emits light, the light is spreading out in all directions. So you've got light coming off in all directions. And so the light is essentially going off, and let's try to make it 3D. The light is going off three-dimensionally, spreading outward in a spherical manner. So originally, this little packet of light, it was a very small sphere. And as it radiates outward, the center becomes hollow because those light particles have left that area, and now they've all moved out. So as they move out, they're going to occupy a larger spherical shell. And that spherical shell is going to keep expanding. And the center, suppose you turn the light off, that shell is going to keep expanding even if no new light is coming out. So it's not a solid sphere of light. It's actually just a shell of light. And so the surface area of a sphere that this light is spreading out over, the formula for surface area of a sphere is, of course, 4 pi r squared. So you've got this certain amount of light, amount of, I cannot write, sorry, amount of flight, this looks like flight, divided by area that it's spreading. Sorry, my handwriting on this mouse is terrible today. And so the total amount of light being emitted is P, the luminous flux, right? And the area that it's spreading out over is the surface area of this sphere. So that's how we got this formula. Now, I do want to make one small caveat. This is assuming that the light spreads out equally in all directions. But frequently, you might have a light mounted on a ceiling, right? And in this case, the light is only coming out downward. So in this case, you've got half the light that would have been, all the light that would have been going up here. There's two possibilities. Possibility number one is all this light is just absorbed and wasted. If that light is absorbed and wasted, then this formula is still valid, because you really only have half of the light coming down. So this formula is still valid. However, frequently, if you look at actual real lights, they put a little mirror above this light so that all of this light here gets reflected down. Okay? And so in that case, you've got this same amount of light, but it's going out over a smaller area. So if that's the case, instead of putting a 4 pi r squared right here, you should put a 2 pi r squared, because the area that it's spreading out over is only half as much. And that's mathematically equivalent to saying that it's the same as if I kind of doubled the brightness of my bulb, right? Because now all the light that was going up is going down, so I've doubled the amount of light coming this way. So cutting this 4 down to a 2, or putting a 2 up here, both accomplish the same thing mathematically, and that will take into consideration if your light is mounted with a mirror reflecting the light. Okay, let's look one example problem here. 200 watt light bulbs, each emitting 1750 lumens, are mounted above your desk on a 2.7 meter high ceiling. So let's kind of draw a little room here. You've got two light bulbs. I guess they're mounted right on top of each other. And this is 2.7 meters high. And then here's your desk, and it is 1 meter high. And then these guys are putting out light. And so it's coming down and it's hitting your desk, right? And so on the surface of your desk, you've got all this light particles hitting your desk. And the question is, what is the illuminance on your desk? So illuminance is the total amount of light divided by 4 pi r squared. Okay, the total amount of light, well, we have two light bulbs, right? Each one is 1750, so that's 2 times 1750. And then in this one, it doesn't actually say, this is my fault, I made this question up, I apologize. I didn't specify whether there's a mirror above here or not. Let's assume there is, because in a classroom, typically, there's a mirror here. And so instead of a 4 pi r squared, this we just said is going to be a 2 pi r squared, because the amount of light is getting doubled, aka the amount of area that it's spreading out over is getting cut in half. So 2 pi, and then the radius, if the total height was 2.7 and the desk is 1 meter tall, then the distance away, the radius there, is just 1.7 squared. And so our illuminance, we can cancel those 2's out, and we can go 1750 divided by pi divided by 1.7 divided by 1.7. And I'm getting here 193 lumens per meter squared. Okay, and I'm not sure actually, I should have checked online before I did this, but there's industry standards for how much light needs to be striking a surface for various activities. So for example, in an academic classroom, there's a set standard that has to be achieved for optimal, not optimal, but for learning conditions to be met. Like for example, if you just had one light bulb hanging in the middle of a huge classroom, it wouldn't be an ideal learning condition. Or for different office buildings or things like that, there's certain minimum amounts of illuminance that are required, and so architects, when they're deciding where to put the light fixtures and what size of lights to use, etc., they have to take this into consideration to ensure that enough light is in all the appropriate places. Okay, I guess now is a good time to take a break. I know this lecture is actually not as long as many of the other ones, but we're roughly in the midway point, so feel free to pause and take a break and then come back in a few minutes. So the speed of light is something that you may have never thought about, or you may have already learned in previous classes or been interested in. But typically, the speed of an object or of a particle depends on the speed at which the object that emits that is moving. What I mean by that is, say you throw a baseball, and you can throw it, say, like 30 miles per hour. But if you jump in the back of a truck, and the truck takes off at 20 miles per hour, and then you throw the baseball, even though you threw the baseball at 30 miles per hour, you were already moving at 20, so the total speed of the baseball is going to be 50 because you add the two speeds together. But it turns out that with light, that doesn't occur. It's very complicated, and it leads to a lot of very strange things. But it turns out if you shine a light on, it goes forward at a certain speed. If you jump in the back of a pickup truck and the truck is going forward and you shine a light on, it's also still going at the same speed. It did not gain that additional velocity of whatever the truck was moving. The speed of light will be going the same regardless of whether or not you were moving when you emitted it. So for now, just trust me, kind of, and believe that. And so this was hypothesized first by Einstein. He wasn't able to prove it because they needed, you need to be moving really fast in order for this to be observed. But since then, there's been experimental evidence that has confirmed his theory that is based on the speed of light being constant. And so that constant is something you definitely, absolutely must memorize. It's actually like 2.9979 times 10 to the 8th power, but we're good to use 3 times 10 to the 8th meters per second. And the symbol that we use is C. So it's in lots and lots of formulas, the speed of light, and we'll just use the letter C for the speed of light. I don't know why we don't use S. I think S is usually used for a variable. I don't know. Whatever. Anyway, C is the speed of light. Learn it, love it, and memorize it. Okay, so most of up until that point was thinking of light as a particle, and now we're going to talk briefly about what happens when you think of light as a wave. We already said that waves have things like a wavelength and a frequency and a velocity. So the velocity is the speed of light, but there is a wavelength and a frequency, and then there are different properties of lights there are different properties of light waves that you can only understand by thinking of light as a wave, and if you tried to think of light as a particle, it wouldn't make any sense. So one example is called diffraction. So when light passes near a barrier that's roughly the same size as its own wavelength, it will interact with that object and it will bend. So the particles in a cloud are very small, just like single molecules, and so light passing around the edges of clouds can diffract. And then this is an example of light passing around a ball. This ball right here would have to be really, really tiny. I mean, it looks like a racquetball or something. So if light was hitting a racquetball, this would not happen. But if light is hitting a super, super tiny ball, like a single atom or something, the light, some of it will pass around this side, some of it will pass around this side, and those two passing beams of light will interfere with each other, causing interference patterns and diffraction, and spreading out of a light beam like this. It won't just be a laser beam straight forward anymore. It will spread out like that. So diffraction is light spreading out and bending around a barrier, and we're going to go through that in glorious detail in chapter 19. Lots and lots of detail. Okay. Another thing is color. So the different colors of light are actually based on the wavelength of the light. So the only way that you can obviously understand the wavelength of light is to think of it as a wave. And so light can have a very, very wide range of wavelengths. You may have heard of, obviously, visible light, but you also heard of ultraviolet, X-rays, infrared, radar, TV, shortwave antennas, AM radio and FM radio, gamma rays. All of these different kind of rays are technically light waves. The human eye, though, is only sensitive to a very small range of frequencies or wavelengths. So the human eye is sensitive to roughly 400 to 700 nanometers in size. You should probably memorize that the human eyeball has a range of 400 to 700 nanometers. Obviously, every person is a little bit different, but that's the general visible range. If light falls outside of that spectrum, human eye cannot detect it. But of course, that doesn't mean we can't detect it using other instruments. You've probably heard of a radio telescope that detects radio waves, or infrared cameras, things like that. They're detecting light radiation that's outside of the human spectrum. So, the velocity, we already said, for any wave is the wavelength times the frequency. So for light, you put in the speed of light, which is going to be c, and then you've got wavelength and frequency. So you can see right away that if you plug in wavelengths of 400 to 700 nanometers right here, the frequency that you get out is going to be very, very, very large. We're talking like something times 10 to the 15th power, roughly. So the frequency, the rate that these waves are oscillating back and forth is like 1,000,000 billion times per second. So they're oscillating really, really, really fast up and down, up and down. So that's just something to take into consideration, I guess, and kind of is amazing. The second thing about color is that the human eye, when you get multiple colors coming in at the same time, we perceive it differently. So you can have pure blue light, which is a bunch of light that all has a wavelength of like 430 or something like that. And you can have pure green light, which is all a bunch of wavelength 530, something like that, right? And you can have pure, what is this called? I think cyan light, that's all like, I don't know, 490, something like that. But if the human eye if you shine blue and green both on the human eye, and you don't shine any of this, the human eye still, to the human eye, the combination of these two makes it look as if this was being shown. So here's a color wheel, and it shows that if you shine blue and green at the same time together, what you perceive is this. That doesn't actually mean that you're having this wavelength of light coming into your eyeball, but it means that's what it looks like to you. It's as if that's what you're observing. And so, we have rods and cones in our eyeballs that are light sensitive and color sensitive intensities. And so the combination, that's very complex, but the combination of different colors is perceived by the human eye is a certain color. Same thing if you add green and red, you'll get yellow. If you add red and blue, you'll get magenta. If you add all three colors, the human eye will observe it as white. So white light is a combination of multiple different wavelengths. You could also add yellow and blue to get white, or you could add red and cyan to get white, because the cyan itself is equivalent to green and blue. So different combinations of visible light wavelengths will lead to white or other seeming apparent colors. Okay, so emission versus absorption of light. There's two ways that you can see color. One is if the light is being emitted, and different colors of light being emitted all combine together to lead to a new color. So when you combine multiple sources of emitted light, the light intensity gets brighter and brighter and brighter, and if you add enough different colors in the right combination, it'll eventually always become white. Okay, so the three primary colors are red, green, and blue, as we just saw previous slide right here, red, green, and blue. Those are the primary three colors that are combined together to form all the other colors. And so this is how all of our screens work, our TVs, our computer screens, etc., etc. There's three different color emitting pixels in the screen, and they control the ratio of red to green to blue. And so, right here in this white zone, it's actually shining. It's literally shining red, green, and blue. And interestingly enough, if you have a VGA cable or something plugging into your monitor and you wiggle it just right and you disconnect some of the pins, some of the colors will no longer be transmitted, and you'll see this, like it might turn yellow. For example, if the blue, if the VGA pin that is transmitting the information for the blue color, if that disconnects, then you wipe out blue. This all turns black because there's no more blue there. this will turn red, this will turn green, and this will turn yellow. So it's kind of interesting. I've had that happen before, and it was actually kind of cool, almost as an accidental demo. Okay, so that's light being emitted. The second option is that light could be absorbed. And as we said, most everyday objects, the light is hitting it and bouncing off. And so in that case, the color you see is actually whatever light is being reflected, not whatever light is being absorbed. So the color you see, so suppose you see something that's green, right? If you see something that's green, let's go back to the color wheel. If you see something green, that means, sorry, let me start with saying, if you shine white light, like the light you get from a regular light bulb is white light covering a wide spectrum. If you shine that on something that looks green, in order to look green, all the red and all the blue had to get absorbed out of it. Okay, so whatever color you see is the leftover after the other colors have been absorbed. And the more pigments you add, the more different colors you add, like the more paint that you add together if you're painting a picture, the darker it gets. And the reason is because every time you add a color, you're absorbing more and more of the light, allowing less and less to be reflected. So when you add more and more pigment or paint, your paint is going to get darker and darker and eventually be black. Whereas if you add more and more sources of light, it's going to get brighter and brighter and eventually become white. So your primary pigments are the opposite of the primary colors. The primary pigments are the yellow, the cyan, and the magenta, because each of those only absorbs one color. So yellow, let's take a look. A yellow pigment reflects red and green and absorbs blue. So if you see something that looks yellow, that means that the particles that it's made of are absorbing blue light. So for example, a banana peel, if you shine white light on a banana peel, the banana peel is absorbing all of the blue, extracting it, leaving behind the red and the green to get reflected, and that combination of red and green that gets reflected, the red and green that gets reflected combines to appear yellow to you. So that's a very interesting way that the colors work out. So you can ask yourself questions like, what color would a banana look if I shone red light on it, or green light on it, or just blue? So let's answer that question. What color would a yellow banana look if I shone just red, just green, or just blue light? Okay, so a yellow banana reflects yellow, which means it reflects red and green. So if you shone only green light, the yellow banana reflects green, and so the entire banana would appear green. If you shine red light on a banana, the yellow banana reflects red, so the entire banana would appear red. If you shine blue on a banana, the yellow banana absorbs blue, and so all the light that was being shown on the banana would get absorbed, and the banana would look black. And if you have a blue light, you can try that. Shine a blue light onto a banana, and it will look black. Or just a t-shirt, if you have a t-shirt with different colors, you can go and shine a blue light on it or a red light, and certain colors will just completely disappear and turn black, and other ones will turn the color of the light that you're shining on it. Okay, let's keep going. So that's on color. Oh, I want to mention, you should actually read pages 440 through 442. They do a really good job explaining the difference between the pigment color absorption and light emission, and different examples of the color wheel and how things can combine. Okay, so final note on color. I think I mentioned this before, but I want to emphasize it. You can get pure colors of a given wavelength of any kind of light. So in the visible spectrum, if you see red, it might actually be light that's 700. If you see orange, it might actually be light that's 600. If you see green, it might actually be light that's 530. But it also could be a combination of the primary pigments. Particularly if you're looking at a computer screen or a TV screen or something like that, then if you see orange, you're definitely not actually seeing the orange wavelength of light hitting your eye. You're seeing a combination of the other wavelengths that are combining to look orange. And so just bear that in the back of your mind when you see light. The color is based on the wavelength, but not always directly correlated because multiple things could be combining to appear to be a different color. All right, continuing on ahead with thinking of light as a wave, there's a thing called polarization. So you've probably heard of Polaroid glasses or polarized sunglasses that can protect your eyes from the sun. It turns out that light waves are actually oscillating electric and magnetic fields. So I'm glossing over polarization now because when we learn about electric and magnetic fields, I'll spend a lot more time talking about polarization. But for now, just know that light is made up of electric and magnetic fields. and these fields have certain orientations. And so by passing this light or electric and magnetic field through a polarizer, you can control the orientation of those electric and magnetic fields. And so there's other things in nature that cause certain orientations of these electric and magnetic fields. One of the most important ones is glare. So when light reflects off of a metallic surface, it reflects in such a way that all of the light electric and magnetic fields are oriented a certain way. And if you use polarizing sunglasses that can block that particular orientation of light, then they'll let regular light through that's oriented in a different direction, but all the glare that has a certain orientation, the polarizers, if you orient them correctly relative to that light, it'll block all of that light. So polarizers only allow certain orientations of light to go through, and if you know a certain orientation you want to block, you can set up your polarizer to block specific orientations of light. And you can read all about this on page 443. There's an equation that allows you to calculate the amount of light transmitted through polarizers. We're not going to be doing that. I just want you to know the concept that a polarizer controls the orientation of the electric and magnetic fields that come through, and you can use that to cut down on glare or cut down on other specific types of orientations of light. Last thing is the Doppler effect, which you might be saying, hey, we've already done this, and we have indeed already done the Doppler effect for sound, but the Doppler effect for light is a little bit different. And the reason is, for sound, the Doppler effect depended on the speed of the sound wave passing through air or whatever medium it was in, but the speed of light is constant. So whereas in the other one, the speed or the frequency shift depended on the velocity of the material, the velocity of the wave in the material, for light it doesn't. The speed of light is constant, and that actually simplifies our formulas a little bit. And if we also make the assumption that the objects are not traveling close to the speed of light, so if objects are pretty much quite a bit slower than the speed of light, let's say the velocity is less than 0.1 times the speed of light, so 1/10 or less the speed of light, then this approximation is pretty good. The observed frequency equals the actual frequency or emitted frequency times 1 plus or minus this ratio V over C. So if you're going 10% the speed of light, then V over C is 0.1. You'll observe 10% higher shift. So it's a direct relation, which is actually kind of nice. If they're moving towards each other, the frequency gets higher. This is the exact same reasoning for light waves as it was for sound waves. If the two sources are moving towards each other, the wavelengths will be shorter and the waves will be closer together, higher frequency. If they're moving away from each other, or you're behind something, if you're over here and it's moving away from you, the waves will be more spread out, which is a longer wavelength and therefore a lower frequency. But frequently, with the Doppler effect for light, you talk about a wavelength shift rather than a frequency shift, because with frequency of sound, you're listening to it, so talking about the frequency is very useful. With light, the color of light is based on the wavelength, and so it's frequently converted from frequency shifts to wavelength shifts. And the way that you do that is actually very simple. If the frequency goes up, the wavelength goes down. So instead of a plus sign right here, it's a minus sign. Mathematically, this is just an approximation. It's not mathematically perfectly true that leads to that. But again, if you're going much slower than the speed of light, then this approximation is valid. So the observed wavelength, if two things are moving towards each other, will be decreased, and the observed wavelength, if two things are moving away, will be increased. So if they're moving away, they get a longer wavelength. And I want to tell you what that's called. Let me go to the picture here, actually. We said if they're moving away, the wavelength gets longer, right? So if they're moving away, you're shifting that way. So I'll write here, moving away. If you're moving away, if two things are spreading apart, the observed wavelength that you see is moved towards a longer wavelength. And this side is red. And so it's called red shifted. You might have heard of red shift and blue shift. That's what they're referring to. When you look at the Doppler effect for things that are moving apart relative at slow speeds relative to the speed of light, then you can see a red shift, which is very kind of cool. So when you look at different stars in the sky, if they're moving away from you very rapidly, the light that we see from them it's not actually have to be red, but it's shifted towards the red side of the spectrum. So purple might look blue, blue might look green, green might look yellow, yellow might look red. It's shifted a certain amount in that direction. And then likewise, if two things are coming together, you shift the other way towards lower wavelengths or shorter wavelengths, and that's called blue shift. So let me get back to that slide here. So when things are moving away, the wavelength gets longer, and that's red shift. So things are moving away, red shift. If things are moving towards, that's blue shift, as we just explained. So when you talk about astronomy, that's when you most frequently talk about red shift and blue shift, and you can use this to figure out how fast things are going towards Earth or away from Earth by observing them through a telescope and measuring the spectral lines emitted. So let's do an example problem. I made this one up, but it should be relatively reasonable and accurate. So suppose that regular hydrogen in a laboratory setting emits a spectral line at 656 nanometers. If you don't remember spectral lines from chemistry, basically when the atoms go from an excited state down to the ground state, they emit a photon with a certain energy and therefore a certain wavelength. And so you can look at different atoms, and based on their atomic structure and elements energy levels, you can write down or record the different wavelengths of light that they emit. And so you can get a pattern, a known pattern, and so you can look for that pattern shifted by a certain amount, and then you can say, okay, that's got to be made of hydrogen, but since it's shifted by a certain amount, it must be moving towards us or away from us at a certain velocity. So this example problem talks about that. So normally it would be coming out at 656 nanometers, but suppose we observe a distant galaxy and measure its spectral line at 644 nanometers. So can we tell if the galaxy is approaching or receding? The wavelength actually got shorter. Okay, so if the wavelength is getting shorter, that means the two objects must be coming together. So that means that the galaxy must be approaching us. Is that called a red shift or a blue shift? Well, if you remember that 400 is blue and 700 roughly is red, then if you shift from 656 down to 644, you're shifting in that direction. So it's a blue shift. And again, approaching things are a blue shift always, and receding things are a red shift always. So can we figure out the speed of the galaxy? Why, yes, we can. So we know that the galaxy is approaching us, and we know the wavelengths. So let's check the formula that we're going to use. We're going to use the wavelength formula for things that are moving towards each other. So lambda observed equals lambda actual times 1 minus v over c. So lambda observed equals lambda actual times 1 minus v over c. Okay? And now we want to solve this, and we're trying to find the approximate speed of the galaxy. So we're trying to solve for this variable v. I'm going to do it algebraically first. I'm going to divide both sides by lambda actual. So I've got lambda observed over lambda actual equals 1 minus v over c. Then I can subtract 1 from both sides. Cancel, cancel. Subtract 1 from this side. And then I can multiply both sides by c. Cancel, cancel. And finally, I get negative velocity equals c times negative 1 plus lambda observed over lambda actual. Sorry, I'm running out of space. And then if I just multiply this side by negative and negative, it solves it for me. So the velocity equals c times, negative c times negative 1 plus, and then y observed is only 644, whereas lambda actual should be 656. And so my velocity, I can type this in my calculator, and typically you'll leave your answer in terms of c, so you can leave the c as a c. So 644 divided by 656 equals minus 1 equals 0.0183 c. So the speed of light is 1.8% of the speed of light. Let's see what that actually is. Times 3 to the 10 to the 8th. That's actually really, really fast. So that's like 5,500,000 meters per second. So, it's a very small answer if you look at it in terms of the speed of light, but it's really, really, really fast if you think about it in terms of just actual speed. 5.5 million meters per second. That's 5.5 thousand kilometers per second. 5.5 thousand kilometers per second. So that's very, very fast. Anyways, and it's coming toward us at that speed. So when you're talking about galaxies, they do move towards each other really fast because they're so far apart and the whole universe is, well, it's actually expanding, not coming towards each other. But locally there might be galaxies coming towards each other. So that's the Doppler effect. It's extraordinarily useful in calculating the speed and direction of galaxies moving relative to ours, and it's been very pivotal in astronomy and astrophysics. Okay, so just a summary, key concepts from chapter 16. If we think of light as a particle, it's going to travel in a straight line as a ray until it hits something, and it's either going to bounce off or go through. The light spreads out uniformly in a spherical shape, giving us this formula E equals P over 4 pi r squared, where P is the total amount of light emitted, 4 pi r squared is the shell that it's expanding over, and E is the illuminance hitting a surface. The speed of light is constant. We use the letter c to represent that, and the numerical value you should be memorizing is 3.0 times 10 to the 8th meters per second. Light has many properties that we'll study in detail in the coming chapters. For example, diffraction, polarization, interference, reflection, refraction, all that kind of stuff. And each of those is going to be its own subunit in the coming chapters. The next thing is that colors that humans see is based on the frequency and or wavelength. Typically, I mean, frequency and wavelength are interrelated, so if you know one, you can find the other. But typically we use wavelength to characterize the light, and the range that humans see is again 400 to 700 nanometers. 400 being blue and 700 being red. And then the Doppler effect, which we just talked about. So that wraps up chapter 16. And then next we'll dive into chapter 17, 18, and 19, which are all the very specific effects of light.